And I could probably spend the next 20 minutes talking about all of the awards he's won, but I'll just list a couple to keep it brief. But he was awarded the Forbes 30 Under 30 for Science in 2020. And he was also awarded the Dr. Pliny and Margaret H. Price Award from Ohio State, also in 2020. Thank you for joining us, Carl, and take it away.
Awesome. Great. Yeah, I'm very thankful to be with y'all today and to share a bit about what I've been focusing on for my research. I can't see the chat, so feel free to send comments there or clarifications, and I think folks are going to let me know as they come in. But today I want to talk a bit about some of the things I've been interested in terms of the death of massive stars and some of the different pieces that we're trying to simulate as well as connect to observations. But yeah, I'm really excited to talk about some of these things today. So I like to start off with sort of an overview to give an idea of where I'll be going with this talk today. I'll start with some introductory material, try to get us all on the same page about why I'm interested in these objects and core collapse supernovae in general. I'll talk a bit about how we understand these explosions to take place, and I'll also talk about some of the problems, the open challenges that we have in the simulation community, and some of the implications that they have for our predictive power in terms of the astrophysical observables. That'll motivate some of the work that I've done recently, looking at 3D core collapse progenitor models, where we're looking primarily at massive stars in these final moments before collapse to gain a better understanding of what this structure looks like and how that plays a role in that mechanism. Where I'll present a few results from a handful of 3D progenitors on rotating. I'll speak about a new 3D rotating model that we just recently published, and then also mention some of the implications that they have for signals of core collapse supernovae and some of the future prospects we have for these signals. And since I've already used this abbreviation quite a few times, CCSNe, that's core collapse supernovae, so it's the plural of core collapse. I'll be using this acronym quite a bit, but we're talking about the explosions of massive stars. And I'll go into more detail in the talk about what those look like. And so the general idea is that we can categorize stars in a ton of different ways, but some of the ways that I like to think about it is in terms of low mass stars and massive stars, or in this diagram shown here, high mass stars, where the low mass might be something similar to like our sun, or maybe a few times the mass of the sun, that'll produce some or leave behind some compact remnant, whether it's a white dwarf or a system of two white dwarfs that eventually merge. And then you have sort of the high mass stars shown at the top here, where we have a main sequence star, becomes a red supergiant or a supergiant in general. It explodes and then leaves behind, neutron star or a black hole, depending on sort of the initial conditions of the stellar model or this star. I'll be focusing primarily on high mass stars, as in this diagram, or massive stars, about stars that are about 8 to 9 times more massive than our own sun. And so I like to orient some of the motivation that we have for studying these massive stars by looking at some of these observational events that have taken place that have been very groundbreaking in different ways. And so the first here is this observation of a neutron star merger, where we have sort of the afterglow of this event. One of the things that was very novel about this event was gravitational wave events. We saw it first in gravitational waves, GW 170817. This is sort of a qualitative plot here shown of this gravitational wave signal, these two neutron stars merging. And then there was subsequent optical follow-up with that. But it was very groundbreaking because it was the first time that we were able to detect gravitational wave signal as well as the optical sort of counterpart to this event. Excuse me. So I also like to think about events like supernova 1987A, shown here on the right, where we were able to observe this sort of this supernova explosion and start to ask some questions about what we expect about the progenitor or other types properties of this actual explosion. So this one was very novel in this way, in that it was the first time that we were able to detect an astrophysical source of neutrinos from something other than the sun. And so there's a handful of neutrinos that were detected here from this event. So again, coupling things from different sources to gain a better understanding of these astronomical events, both of which rely directly on our understanding of stars and how stars may end their life. And so I'll go into detail now a bit about core collapse supernovae, which are sort of the progenitors of both of these events in most cases, and some of the things that motivate our studying of these scenarios. So the death of a massive star can sort of look like a lot of things, and in most cases it can produce a stellar transient, one of which is core collapse supernovae. So I'll describe what that is sort of a little bit further, but they can also produce other catastrophic events such as collapse stars, gamma ray bursts, or very superluminous supernovae, all depending on a bunch of different properties. We're also interested in the compact objects that they form, right? Understanding the type of remnant that they leave behind has implications for the signals they might produce, whether it's double neutron star system or other such things, or can it build a stellar mass black hole, to an appreciable size. These are all things that require an understanding of the explosion or the end fate of a massive star. Galactical chemical evolution is also influenced by some of these things that we study relevant to these massive stars and the end of their lives, and those play a very important role in those areas as well. And one of the things that I've started to think about more deeply lately is multi-messenger astronomy, in particular the gravitational wave signals that these explosion simulations might produce, as well as the neutrinos, and of course sort of next generation electromagnetic predictions for what these models produce, and bridging sort of the connection to these sort of large scale 3D explosion simulations to the final sort of end product of this shock breakout and other properties that we can predict from them. So in general, when we're talking about core collapse supernovae, we expect that they're about a few per century for a Milky Way type galaxy. They liberate a ton of neutrinos, and they have kinetic energies on the order of about 1 × 10⁻51 erg, so about 1 beta. So they're very energetic. And then, so as I mentioned a bit earlier, they're produced by stars with a mass about 8 to 9 times more massive than the sun, so massive stars. And so to understand sort of what produced these core collapse supernovae, we have to think deeply about the final moments of a massive star and what that looks like to connect our picture to these things that we observe. And so here I have everyone's favorite picture of a massive star, sort of this simplified onion model here, where you have an iron core at the center, where it's produced primarily of iron peak nuclei, and then around that is previous burning stages of silicon, oxygen, neon. But the general picture is that massive stars burn heavier and heavier elements as they evolve in time, eventually building this iron core. The silicon burning shell that is above this iron core from a previous burning stage continues to grow this iron core that is primarily inert at this point. So it's no longer going through fusion in the same way. And so eventually this iron core reaches a maximum mass, and then it becomes gravitationally unstable, and then it begins to collapse dynamically, ushering in sort of the end of the life of this massive star. And so we can take this generalized picture from this onion model of this iron core in that moment at the start of collapse. We can sort of detail some of the properties of how stellar collapse plays out, where here we have that sort of iron core increased in size. It has some radius of about 2,000 kilometers, some central density. And so this core begins to collapse or become unstable and fall inward. And that happens on the order of about 250 milliseconds. So about 0.3 seconds, this collapse takes place. But eventually it collapses down, and then it stops at a certain point. It stops when the radius is about 50 kilometers. It forms this protoneutron star in most cases that has some very large central density, shown there about 10 to the 14 grams per centimeter cubed. And so when it stops, it doesn't just stop, it sort of creates this bounce. And so this is sort of the bounce point of the collapse that folks like to talk about, where this infall has reached the point where it stops, and eventually a shock is generated due to this bounce, where the core has continued to stop falling inward primarily. The shock is sort of produced to move outward. And if it's energetic enough, or at least folks sort of had these ideas in some of the early literature, that this bounce shock that was sort of generated can actually travel outward and unbind the stellar envelope. But what folks began to find is that there's not enough energy created in this initial bounce to promptly explode the star. And so this is the idea of sort of the prompt explosion mechanism. But it turns out it's a little more sophisticated than that. What folks found is that you have this creation of this shock, but eventually this shock moves from the bounce to this stalled shock phase where it travels outward, it loses energy, and then it can potentially just stagnate and just sort of sit there. And so the question is, how do you go from the bounce to creating this shock to having the shock stagnate to something like you have on the right here, which is a full 3D core collapse explosion simulation, where we have that progeneutron star in the center again. The dashed white line actually shows where the shock is stagnated. And then in the center, that progeneutron star is emitting neutrinos. And so you have this stalled shock, and the question is, how can you revive this stalled shock? And so a lot of the ways that folks like to think about this, or at least for the majority of explosions, the idea is that you can have neutrinos drive the explosion, where here in this diagram on the right, we show the progeneutron star in the center, some mass falling inward from the still collapsing star. But the general idea in that center is that you can have a region where the shock is actually being heated up, and eventually you can heat it up enough that it can continue to expand outward and drive explosion. And so what you do is you tap into some of the energy that is emitted as this progeneutron star begins to contract and release these neutrinos, and that's what we call the delayed neutrino driven heating mechanism. And so it's this shock absorbing the neutrinos emitted from the progeneutron star in the center. And this is the mechanism by which we believe that a large majority of massive stars can actually drive successful explosion. You only need a few percent of the neutrinos that are released to actually drive this explosion. Something by Ben and Wilson in 1985. And so this is sort of the general paradigm that we see in our explosion simulations. And so moving forward, this sort of mechanism for exploding, you can imagine that there are some pieces that go into how you might simulate that when you try to take all of these things into account. So here I'm showing a bunch of my favorite 3D volume renderings of different explosion simulations, where we're focusing on visualizing entropy here, mainly because entropy allows us to visualize that protoneutron star in the center. So that core piece that we know can actually provide that heating mechanism to drive the shock. And then above that is the actual shock morphology in a range of different initial conditions for these explosion simulations. But this diagram on the top left shows sort of all the pieces that kind of go into these 3D explosion simulations, where you have to consider potentially magnetohydrodynamics, so magnetic fields, general relativity, so whether you make an approximation for that or you do the full sort of GR implementation. Neutrino transport is very important, as that's the primary heating source. And there's also uncertainty that goes into microphysics. And so a lot of these sort of go into these models, and you try to use the most sophisticated methods for these, but at some level you'll have to make an approximation to be able to run these simulations in something and take advantage of those current computational resources that are offered. And so some of the open challengings are sort of motivated by some of the uncertainties in the approximations that you place into your 3D model. And so here I have sort of visualizing one of the open challenges that we have for these simulations is that you'll take a 1D stellar evolution model for the pre-supernova evolution. You'll map it into your multi-physics code that has all these different pieces of physics that go into it. And then you'll explode the model, as we're showing here on the right, by this volume rendering of the entropy again, showing the explosion of a 20 solar mass star. But eventually you have a simulation where, or a situation in this particular model, where the shock fails to be revived. So remember, we have that sort of mechanism that allows shock neutrinos to be absorbed to heat the shock, but in some cases that is not efficient enough. And so you have a shock that stagnates, And then in this particular model, it actually begins sloshing, something called the standing accretion shock instability, or SASI. But the overall qualitative result is that this model fails, despite having some of the, most of the state-of-the-art tools in terms of neutrino transport, gravity, and other things. So the question is, why is this shock not being revived? And what can we do in our models to get something closer to what we expect for this model to explode? Another point of contention is that there are challenges that even when you have the model explode, as shown by this diagram here on the right by Adam Burrows' group in 2019, where on the x-axis we have the post-bounce time. So this is sort of a measure that we use for the start of the explosion. And the y-axis is the diagnostic energy, which is a proxy for the explosion energy. And so for most of these different colors in these line graphs, you notice that they're still sort of increasing in time. But the one I'll point you to is sort of this green line, or the one that's sort of been evolved the longest and started to asymptote. But it reaches a value of about 0.1 beta, or 10, 0.1 times 10 to the 51 ergs. And so this is actually below what we expect the explosion energies to be for this range of for progenitor models for different masses. And so the question is now, even if we're able to explode the models with their 3D simulations, where these diagnostic energies were produced from a grid of 3D explosion models, they're energetic. So they're missing some energy, if you will. And so something is missing where we're getting a qualitative result that maybe agrees where we expect these stars to explode, but now we're getting something that doesn't quantitatively agree because these energies are very weak compared to what are inferred by semi-analytical models or from observations. Also, and then we mentioned on the previous page where shock revival, right? So models fail to explode in some cases, where we showed the model from the 2018 paper, Sean Couch's group. And so we're faced with these different dilemmas, these different challenges. Well, if you can get them to explode, they're energetic. If you can't get them to explode, what are we missing here? And then there's also this idea of what does the fate of the compact remnant look like? So can we evolve these models further out in time using these resources or in new novel ways that allow us to make more stricter, more predictive estimates about what that protoneutron star or that black hole might look like, or so on. So using these tools in that same way, these are all challenges that sort of go into modeling core collapse supernovae. And so some of the potential solutions that have been brought up have been proposed by different groups. So for instance, I mentioned GR earlier. Some folks have shown that, when you do full GR instead of a Newtonian potential, for instance, you get more compact neutron stars. That leads to larger neutrino heating. That means that you can more easily revive that stalled shock. So that's one potential solution. The neutrino transport, right? So how you treat the transport, whether it's has an angle dependency or includes other different neutrino physics terms, those are all things that can make a qualitative difference. Folks have shown that, like this simulation on the right, where a work by Luke Roberts in 2016 showed that you can get successful explosion when you include full transport plus GR. That's very computationally challenging to do. And so understanding which piece of that particular combination or sub piece actually contributes, or at least defining how it contributes in that way, is very important. So one of the things that I've been focused on as a potential solution to this as well is the pre-supernova model. So I mentioned earlier that folks take these 1D stellar evolution models, they map them into your multiphysics code, they collapse them and then explode them in 3D. So I'd like to make the argument that stars are not spherical, despite showing that onion model diagram I had earlier. But I'd like to argue that this has appreciable impact on many different characteristics of the explosion. Is it something that we need to look more closely at? And so in 2015, there's actually a work that looked at this particular thing in the context of core collapse supernovae. And so Sean Couch's group in 2015, what they did was they evolved for the final 3 minutes before core collapse, a 3D massive star model. And so in this particular simulation, they only did an octant, so 1/8 of the full 4 pi star. But they were able to do a few things. They were able to show that the silicon shell deep within that, we'll call it, that sort of is what grows that iron core to its maximum mass, it's very turbulent, and it has convective velocities that are on the order of about 500 kilometers per second. Where here we're visualizing the magnitude of the velocity field in this 3D simulation. Where towards the end, as you move left to right, those speeds get very appreciable. These could all have qualitative impacts if this model is then followed through collapse and then eventually exploded. And so that's what they actually did in this paper. Was they took that 3D initial condition, they followed it through collapse, bounce, and then exploded it. And then they also took an angle average of that 3D initial condition as sort of a proxy to understand what happens when you wash away those perturbations, those non-radial perturbations. And they exploded that as well. We're here on the x-axis, we're showing post-bounce time again. And then the y-axis, we're showing the average shock radius. So this is a proxy that we use to measure if the star is exploding. And so the cyan line shown here, the one at the top, is the 3D initial model. So that 3D progenitor I showed from the previous slide, they collapsed that, exploded it. What they're finding is it's more energetic, meaning the shock is sort of reaching a higher radius at earlier times, and it explodes more promptly. So this radius is moving out much further, as compared to the bottom line, which is that angle average when you wash away those perturbations. And so this is sort of driving the point home that these multi-D progenitors can provide a solution to some of the open challenges that we're facing with modeling core collapse supernovae. And so another work that has looked at doing this was a work by Bernard Muller's group in 2017, where they ran 2 explosion models, so similar to the previous paper I just showed. But on the left, they started from 3D initial conditions, and on the right, they started from 1D initial conditions. So I'll point your attention to the right at first. We're visualizing entropy here, so these are slices trying to look at the shock. But if you look at the sort of right figure first, you might recall that this looks somewhat similar to that sloshing that we saw in our first video that I showed, where the shock has stagnated, some specific modes are excited, and so there's some sloshing that takes place. But eventually this model is no longer, the shock is not revived in this model. This model actually fails to explode. Whereas on the left, you have a shock that is at much larger radii. The scales are actually different between these 2 figures. But you have something that's very asymmetric. You have something that's tending towards an explosion just by using these 3D initial starting conditions. So again, driving that point home that these provide a potential solution. So I think one of the questions that folks have after seeing some of these works is, in the literature, is how do these models help facilitate explosion? So folks have pointed out that if you have these large Mach numbers in the progenitor model, so the model near collapse, so these final moments before collapse that folks are simulating, those can be favorable for explosion because they induce density fluctuations. Those are amplified during collapse. Those are favorable conditions for explosion. You can also think about sort of what is taking place inside the convective region in the explosion models between these 2 simulations, and they're finding that there's an increase in mass within the gain region, which is this region where in between the protoneutron star and the edge of the shock, that is facilitated by non-radial flow. So you're looking for significant non-radial flow that increases mass in the gain region, which inadvertently increases the heating rate. And so that sort of already answers that first question, is when they washed away those non-radial velocity components in the model from Sean Couch's work earlier, that's why the model was different in terms of its shock radius, because they didn't have this increase in mass in the gain region that is helping drive the explosion. So you also want to see an increase in non-radial kinetic energy. So these non-radial flows, you also want them to be at large scales because this was shown to help drive that shock. So these are 3 important things we're looking for when we're trying to consider these massive star progenitor models before collapse. And so this has all prompted a lot of the work that I've been concerned with lately, where we've been looking at how do we model 3D stellar convection near collapse and get a better picture of what the star looks like for this problem of the initial conditions. And so what we've done is we've started with an initial 1D profile like I'm showing here on the left, where we have mass coordinate on the bottom, which is a proxy for the radial coordinate for a stellar model. Spatial axis, where a value of 0 means the center of the star, and you move out means how much of the mass you have enclosed. Where the top panel is showing the electron fraction, and on the bottom is showing the central density. The main thing I like to point out for these is sort of annotated by the top is that you have the iron core included, and then we have silicon, oxygen, and neon sometimes for the different shells that are followed, in these simulations. And this dashed white line actually shows the edge of our domain. And this is for a 15 solar mass model. And so you start with something like this, a few minutes before collapse, you map that into Flash, and then you can realize something like this, where we have a 3D simulation of the final moments near collapse, where we're visualizing here the magnitude of the velocity field within the oxygen shell region. And so in the center, we have that iron core as it starts to collapse. And so it's steady for a while, it grows in mass and then eventually becomes dynamically unstable. And then that's when our simulation stops. But we're able to capture a picture of what the oxygen shell looks like in this simulation near collapse, and then use that to build a better picture of our initial conditions. We wanted to extend this a bit further beyond just sort of a 15 solar mass model. And so here I have a more complex version of the diagram I showed previously, where again, we have the mass coordinate on the x-axis. At the top, we have velocity, and then oxygen and silicon-28 for each panel below that. The main thing I like to point out about these is that we survey a range of initial conditions, because in 1D stellar models, you'll have a range of sort of oxygen shell widths or silicon shell widths, as well as convective velocity speeds. So we wanted to extend our survey and actually look at a range of initial conditions that might be realized out of a grid of stellar models that have all varying initial conditions. And so we use these initial conditions as our basis to evolve for the final 10 minutes before collapse in a similar way, doing the full 4-pi 3D simulation, but building on previous work where we're evolving longer and able to catch more convective turnover times in these different models. And so when you do that, we can actually look at the different properties here, where here from left to right, I have the silicon-28 mass fraction. The middle panel is the radial velocity, and on the rightmost, we have the radial Mach number. And from top to bottom, we have the 14, 20, and 25 solar mass model. The main thing I like to point out about these is that they're all qualitatively a little different. The 14 solar mass model kind of takes a while to get started up. Convection is weaker. It has a more narrow oxygen shell. The 20 solar mass model in that middle panel is very energetic. A lot of mixing taking place in this particular model, and it has very large speeds. And then on the bottom is the 25 solar mass model, which has something about in between those two models. So we're observing large scale flow, and we're also sort of reminded about looking for Mach numbers that are appreciable in these different shell regions, which is again that rightmost panel that has implications for sort of the explodability of these models. One of the things that we've also been excited about being able to do with these 3D simulations is that you can use them to sort of fold back and inform the 1D MESA models or approximations in some cases. And so on the right here, I have profile plots showing the mass coordinate on the x-axis for the spatial coordinate. On the top is the convective velocity. And so the solid line in this particular diagram corresponds to an angle average of the 3D simulation. So one of the simulations in the previous slide, we took an angle average of that. This is a snapshot 5 seconds before collapse. That dashed line is actually the MESA model corresponding to that same time. So we're noticing a few things. We're noticing that the convective velocity is much less in the MESA model, so a factor of 2 maybe. And then also there's some difference in the extent of the oxygen shell region, where this is the main sort of region that's being shown here. That bottom panel is the same differences between the 3D angle average, and the dashed line is the MESA model. And so things I like to point out with the sort of the bottom panel, where we're looking at the mass fraction here. So where is what, if you will, about the carbon and oxygen for these profiles. So if you look at a radial coordinate of about spatial coordinate of about 3.6 to 4.2, so the edge of that oxygen shell, which is the pink line, there are these sharp features that are observed in the MESA model. that are sort of outcomes of how mixing and other things are treated in 1D. These are smoothed away in 3 dimensions when you evolve them in this way. And this can definitely have implications for things like mixing in real stars or sort of any type of chemical enrichment that might take place. And so when you can use these data from these 3D stellar models to not only have better initial conditions for explosions, you can also start to measure things that are relevant and helping to inform and help us build better massive star models that we can use in things outside of the context of core collapse supernovae. Oops. Yeah, so it allows us to measure mixing at chemical boundaries. So talking a little bit more about the mixing at these boundaries, here we have some slice plots of the carbon-12 mass fraction. So this is for 2 3D models that we ran, where we're increasing in time from left to right, where the last slice is the final time step that we have before core collapse starts. And so what we're seeing here is the the carbon-12 shell. So this is sort of the white region that's at the outermost kind of part. Below that is the oxygen shell region. So that's kind of the things that I've been showing visualizations of, where we have some carbon being mixed down into this oxygen shell, where sort of the qualitative differences between the top panel and the bottom panel is that you can argue that maybe there's a sort of an increase in mixing or pulling down or entrainment of the carbon-12 into the oxygen shell. In the top rightmost panel, I used to have an arrow for it, I don't know where it went. But one of the things that we found between these models is that how you initialize these, the velocity field in these pre-supernova models, that can quantitatively impact the mass entrainment rate. And so the top panel is just our baseline model. The bottom is a model that was initialized in a slightly different way in terms of the initial velocity field. The reason this is important is because if you entrain more material, say of carbon or something, into the oxygen shell, that can have implications for galactical chemical evolution models. For instance, in very large mass entrainment rates, they found that it could help sort of explain a underproduction of certain odd Z elements. And so again, so not only are we measuring mixing, but we're starting to look at things like entrainment and what we might observe from our simulations and what those implications have for things outside of their explosion. And so this is something that I don't want to say fell out of our model, but enable us to start to measure and continually connect these simulations to other areas of astrophysics of where there is relevance. So one of the things that I've been excited about working on lately is rotation. And so this is like the 2 questions folks always ask about: what about rotation or magnetic fields? We started talking about rotation where on the right, I'm visualizing a 3D model that we just recently put out, where it's a rapidly rotating 16 solar mass star, where we're visualizing neon 20 over here that's kind of tracing how oxygen shell burning is happening in this rotating stellar model. Again, we have that iron core in the center. But what we are observing in these results is that you have angular momentum being redistributed in a way that is potentially outside of what the 1D models predict. And the reason that we're really excited about observing this or kind of seeing what the 3D model tends to is because folks use the profiles of these pre-supernova models and so on to make estimates about the protoneutron star spin rates for things like binary population codes and so on, and make estimates about protoneutron star spin distributions. And so if we're observing something in 3D that differs significantly from what the 1D models are showing, differs meaning maybe angular momentum is more efficient, where there's convection happening, you can start to observe spin estimate percentage differences on the order of 1 to 5%. And so that's quite small that we found in this particular model. So it's somewhat validating the use of the 1D models. But you can imagine a scenario where you have a very tightly coupled silicon and oxygen shell, which this model did not have, that are very convectively active, that can increase that percent difference to around 10 to 20%. And now you have something where your spin estimates are slightly off. It can potentially alter some of the conclusions that folks make as they use these 1D profiles to inform properties of compact remnants. And so that's why we're really excited to move forward with some of these 3D rotating models and also start to think about rotation or magnetism because we want to build better models and estimates for compact remnants and large, and using 3D to inform some of our estimates about that is something that we're starting to do. So now I want to talk a bit about building new models of stellar explosions and what that looks like. And so for us, I mentioned a bit about sort of how we want to use these as initial conditions for explosion simulations. And so this is a work that we've been pushing on, where we start from that 3D initial condition model from a 15 solar mass model. So starting from these realistic conditions, following that through collapse to bounce, and then exploding it in this way, where on the right, I show sort of the entropy of this simulation as we visualized previously. I'll start over. But this is a 3D explosion model from a 3D initial condition. And so when you have this, you can see something that starts to look more like what we expect these models to look like, as you're not washing away these non-radial perturbations, and you're following things self-consistently as much as possible to build these new models. We're starting to observe shock runaway. So this model is actually going to successfully explode. And so that's not an issue. And then we're hoping to sort of have longer term simulations like this, where we can make predictions about the energies and see if that gets us closer to something that we expect by using these initial conditions, bringing that gap that we have from our models and what observations suggest, bringing those closer together to something that agree. And yeah, so we're really excited with these models to also look at the impact of multi-messenger signals. And so one of the first things that one of the things that folks have been interested in some years with explosion simulations is how, what does the gravitational wave emission look like? And so I'm reminded by the work of Evan O'Connor and Sean Couch in 2018 that actually failed explosion model. Where here on the right, we're showing the gravitational wave amplitude for their spectra for their explosion model, where on the left here we have something that was evolved with no perturbation. So they start with that angle average approximation where there's no non-radial flow, and they explode that model in 3D. And then on the right here, we have something that is evolved with these perturbations. And so what they do is they actually artificially perturb the domain. So they map it in 1D, they follow it for a little bit, and then before this explosion sets in, they sort of perturb the velocity field to sort of mimic what the convective shell burning might look like. And when you do that, you actually observe that when the silicon shell perturbations accrete onto the protoneutron star, it actually causes an amplification of the gravitational wave strength signal over a broad range of frequencies. And so you can start to see that if you want to build, I guess, more realistic core collapse supernova models, you're going to expect that there's going to be some convection occurring in that late stage. And sort of the scale of that is something that we need to start folding into predictions for gravitational wave emission. And so that's something we've been really excited about, and we want to do with our models too. Some of the first steps towards that we've started to do with our 2D simulations. The challenge is that you have to sort of run analogs for that. So if you do for full 3D, starting from 3D, you might want to have 3D starting from the angle average for the comparison. Running twice as many simulations is very challenging. You can do it in 3D though, or 2D simulations, which is what we're showing here, where we have post bounce time on the x-axis again, and we have the plus polarization for the gravitational wave signal at a very optimistic distance. But so the two colors in this diagram show one starting from an angle average, so a MESA model, and then the other one starts from the two-dimensional collapse of a massive star. And so not washing away those perturbations. And again, even in 2D, we're observing that you have this amplification of the signal when that silicon shell accretes that causes an increase in the strain over a broad range of frequencies that we observe for this model. And so building new models means also starting to characterize what these perturbations might look like as you start to build a complete picture of how these models might impact multi-messenger signals. And so one of the things that we sort of like to continue to do is make sure that we are looking at sort of what current detectors can do. And so here I have a diagram from Ko-Chan-Pan's work in 2021, which I think is really good at showing this, where they run actually 3D explosion models with different rotation frequencies. And these explosion models produce gravitational wave emission. They map that into the gravitational wave, the amplitude frequency domain to determine if it can be detected by advanced LIGO or COGRA. And so they have the detector bands shown here, but this is where these signals might lie for I guess, a typical 3D explosion model with rotation. Sort of the general properties that they find is that rotation increases the amplitude of the signal in some cases. But in general, it's pretty high frequency. And so that's sort of some of the motivation arguments for a sort of next generation detector that is able to go to higher frequencies that might help with observing these signals. There's been also work that's been put out where folks have shown that if you combine sort of predictions from low energy neutrinos that you might predict from these explosion signals, you combine that with the gravitational wave signals, you can actually push out the horizon distance to something that's much further out and have an appreciable signal to noise ratio. And so that's something that I'm also excited about too, is how we can combine these different predictive things that come out of our models to help push that horizon distance out and start to see what we can see from these explosion models. Some of the things that I'm excited about moving forward is magnetic fields. I've brought it up a little bit, but folks have shown, this is explosion simulation for Bernard Muller's group in 2021, where they show that even weak to moderate B fields in an otherwise normal core collapse explosion can help amplify convection and actually help drive successful explosion. And so I think a lot of times when folks think about magnetic fields and these progenitor models or even the explosions, they think about these extreme cases where you have these rapidly rotating progenitors. They potentially drive sort of jets and other such things. But I'm really excited about what sort of the canonical massive star might look like, where you might have these weak to moderate B fields that are amplified near collapse and is not energetic as this magneto-rotational driven explosion, but still have a qualitative impact where they show that when you don't include magnetic fields for this model, it fails to explode. When you do, it actually, the shock is revived. And so even the weak to moderate fields can have an impact, and that's something we're excited about pursuing in the future in terms of the progenitor, the pre-supernova phase. And so here I'm actually showing that same 3D rotating model from earlier, where here we have streamlines of what the convection sort of looks like near collapse, where the protoneutron, not the protoneutron, that's an iron core in the center, it hasn't collapsed all the way yet. But you have the streamline sort of tending towards our axis of rotation, which is sort of going this way, if you will. But you can imagine how complex this would become if you have a magnetic field that is initialized in this, and you can start to sort of see how that field grows, what the topology is that it tends toward. So that's something we're excited to really push on in the future, because we think even these weak to moderate fields can have an impact, and we want to move closer towards having a complete picture of massive stars, one that includes rotation and even weak to magnetic fields. And so that's something we're excited to push on. So that brings me to my conclusions. I talked a little bit about how these 3D stellar models of convection can help drive explosion. We observed some large dominant modes near collapse. This is something we show in our paper with these sort of spherical harmonic decompositions for these different shell regions. And we also observed things like mass entrainment, actually, which was shown to have some range depending on your initial conditions, but also suggests that it's more efficient in 3D than 1D models might expect, sort of with the current approximations in 1D. And that's something that, of course, is applicable to things like GCE models and so on, and something we're excited to continue to inform and update with these 3D models. Yeah, the Mach number profiles showed favorable conditions for explosion. That's something that we're excited to sort of show and then start to realize the distribution of Mach numbers you might observe in these 3D models. We also talked a bit about rotation, where in this paper we just put out, we observed that angular momentum sort of redistributes in a way that diverges from MESA, which has huge implications for the remnant, whether it be a protoneutron star mass spin or other such things. And so that's something we're excited to push on even further and start to build a distribution of what you expect from even slow to moderate rotating 3D models. And lastly, we talked about how these 3D explosion models can provide successful input, and also some of the ways that we're trying to quantify where the impact on multi-messenger signals might sort of arise from building these new and I guess more informed models of stellar explosion that take into consideration the state of the star and their collapse. But yeah, there's a lot more we want to push on in that. There are a lot of things I've sort of kept out of the talk. So feel free to ask questions about sort of what piques your interest about this. But there's a lot of things that we're pushing on, and we're excited to move forward in that way. But with that, I will end, happily answer any questions. And I'll also say that our data are online. So the 3D explosion, the 3D progenitors are out there. So if you want to explode them, feel free. Thank you.
That was an awesome talk, Carl. Thank you. And
thank you.
Beautiful your pictures always are. And it looks like Vicky has a question for you.
Hi, thank you for a super interesting talk. So I'm a neutron star person, and I'm curious. You mentioned the initial spins, and you couched in terms of percentage. I didn't really understand what you meant. Like, what is the sort of range of initial neutron star spins that your models have? And then I'm also curious because neutron stars have high space velocities, and can your models reproduce the distribution of neutron star velocities that we observe?
Yeah, that's a great question. So in particular to when I mentioned the percent differences, I was mainly focused on, so there's been papers like Jim Fuller's had some papers out where sort of you take a 1D profile, sort of this pre-supernova profile, and then that's your snapshot for the angular momentum. You integrate from some mass coordinate inward or outward to some mass coordinate, and sort of making assumptions about the conservation of angular momentum, you can predict some protoneutron star mass spin. What we found in our models is that in 3D, the angular momentum profile diverges in some places, particularly those where it's significant or convection is efficient. And so if you're using this basis from these 1D models to make estimates about the natal spin, protoneutron star spin rates, then you could be off by what we found, 1 to 5%. But it could be even larger than that if you have more tightly coupled silicon and oxygen shells, which might come out of looking at a broader range of initial conditions. And so that's mainly what we're focusing on there when folks use these 1D models in that way. And in terms of the second question, I think there's been some work. I think some of the Mueller papers I mentioned, they were able to follow these simulations in 3D out to later times and make estimates about sort of the properties of the neutron star. That's something we're interested in doing in the future, but we haven't been able to do yet. But that's something that's on the to-do list.
Okay, thank you.
Thank you.
If we have any more questions for Carl, feel free to raise your hand or leave them in the chat. It looks like Nicole has a question.
Yeah, I was curious. I agree with Kristen, the visualizations are great. And I was curious what sort of software or packages you use for doing your visualizations.
Yeah, thank you. So I use YT for most of my volume renderings. For this particular, the streamline plot, I started to use ParaView, but I think ParaView is much more challenging to use than YT. And so those are the two primary tools I use. I also use like Visit for like very quick sort of slices and stuff.
I thought I recognized YT. They look great.
Thank you.
Mohit?
Sure. Hey, Carl, amazing talk. I learned a lot personally. Now, I have a couple of questions, but I think looking at the time, I'll ask one. And if we have some time at the end, I can ask the other one. Sure. Now, my first question is regarding the magnetic field. Now, I'm sort of interested in understanding how amplification of pre-shock fields, especially inside the core, works, or is a function, or how it actually evolved as a function of turbulence, mass, and even metallicity. And this question is specifically in my mind because we know the magnetar fields and even neutron star magnetic field is a mystery. So I'm just thinking whether turbulence especially close or inside the core and in your convective models, can help in amplification of the magnetic field, in at least in a subset of neutron stars?
Yeah, so certainly, I think in the particularly in the explosion model that I showed, that's what they were observing. I think I have it here. Yeah, in this model, they ran two, one with MHD, so a magnetic field, one without, and then they found that in this ordinary model, the turbulence was actually able to amplify the field strength to some extent, and then the magnetic field became an appreciable amount of the energy that was involved in driving this explosion. And so it was a still neutrino-driven explosion, but it was sort of helped with this inclusion of magnetism. And so that's for the explosion phase. For the pre-collapse phase, you're right. I think there's a lot that's not sort of understood about what the topology looks like and how that field strength is sort of built or what it tends towards. There's been some work, I know, like even Bernard's group has done a simulation where it's an oxygen shell simulation, so similar to our work, but it has a uniform field in the Z direction. And so they actually are able to sort of show how this helps, and it helps a little bit in terms of the convection and the speeds and so on. But there's a lot sort of there to still be done, and I think there isn't a clear consensus there. So that's why we're excited to start exploring some of those things.
Thank you.
Thanks.
I'll ask the second one if there is no other question. Thanks.
Thanks.
I see Alice has her hand up, and then we have a question from Vicky in the chat, but let's let Alice go first, and then I'll read you Vicky's.
Thanks. Yeah, really great talk. So I'm very interested in gamma ray bursts, and in particular, I'm interested in any relations between like long gamma ray bursts and fast radio bursts. And in particular, whether there might ever be a scenario where you might get some radio burst pre a long gamma ray burst. And so I'm just wondering, I know you didn't touch on this in your talk, and I haven't seen any theoretical work out there, but if there's any kind of space in this work where you might get some type of radio burst now that you're doing these really great 3D models.
Yeah, I think that's a great question. I think for us, we've been focusing mainly, or I've been focusing mainly on, like, I guess, what is the most canonical sort of progenitors. There is some work that I want to do focusing on these extreme progenitors where there's rapid rotation or magnetic field strengths. And so I think there's something there that we're really excited on pushing on. That's why I was kind of starting with this rapidly rotating model in the pre-collapse phase. And so moving to the next step of that is including magnetism. I think that it's a really hard challenge right now being able to evolve these models out to long term. And that's something we're excited to work on at LANL is, okay, the explosion model in most cases isn't even followed out to, say, a few hundred kilometers. But let's move beyond that. And so folks take that as an initial condition, then you map to another code that can evolve much further out, and then you get to shock breakout. So stitching together these different tools to be able to start to answer some of these questions that observers have is something that we're really trying to push on, and is a really big goal of the lab. And I think that's something that could definitely come out of these models as we are able to evolve them to later times and to start to make those predictions. So it's something we want to do. We just are building that infrastructure at the moment.
Yeah, it'd be really exciting. I look forward to hopefully seeing it.
Thank you.
So Vicky asked in the chat, and let's see if we can get this done in 1 minute so we don't keep you too long. But she asked, can binarity have any influence on explosion outcomes?
Yes. So like, it's funny you asked that because like, those are sort of the series of questions like, what about rotation? What about magnetism? What about binarity? And so like, I think it can have a very important impact. Some of the ways that it has an impact, I think would be at different times than maybe some of the ways that I'm focusing on because we're so deep in the core. So we have assumed that these stars are isolated, but that's of course not the case. That is a long-term goal I think we have, but I think there's a lot of work being done with the 1D models where we're starting to look at like, is the envelope stripped or something, and how does that affect sort of the subsequent evolution and stuff. And so I think that, at least in my terms of sort of the things we're starting to look at, that's sort of tied in with looking at like GRB progenitors and stuff, where these new scenarios that might produce sort of unique characteristics as opposed to sort of the canonical progenitors that we really focused on. So it definitely has an impact. yeah, there's a lot of work there to be done.
Okay, thank you.
Thanks.
I don't think we'll have time for your second question, Mohi, but maybe you can follow up offline. And thank you so much, Carl, for joining us.
Awesome. Yeah, thank you again for having me.